Hello! Today we will tackle the process of balancing chemical reactions, chemical equations, and I want to show you a useful trick we often use to adjust coefficients in our equations. This trick can make balancing much easier and more efficient, saving you time and effort in your studies. Let's get started with this essential skill in chemistry. Certainly there are a plethora of ways to even things out, and you can approach it from a variety of different angles and perspectives. For instance, a widely used method is the equalization method, where you go from left to right and equalize the elements one by one. But I feel like this method doesn't always work well because in this case, fractional coefficients can appear. And the fractional coefs are not very convenient. Moreover, in our equations, fractional coefs are not allowed. So basically, our coefficients should always be integers, whole numbers, definitely not fractions under any circumstances. So, how do we work with our equations? All right, let's take a look at the method of equalization using the least common multiple. For example, let's say we have a reaction between aluminum and oxygen. So what do we need to demonstrate here initially? Let's assume we have aluminum undergoing a reaction with oxygen. During this reaction, aluminum oxide is formed. Just a reminder, on the left side we have the reacting substances, the reagents. And on the right we have the reaction products, in this case it's aluminum oxide. So where should we start? Listen up, the first rule states that we got to start with the element whose index is bigger, and oxygen is the one with the biggest index. Please have a look, the value here is 3 and the value here is 2. Additionally, he is the largest value based on the index position. Now what do we need to do with this item next? In order to solve this problem, we have to find the least common multiple of the given numbers. When considering the numbers 2 and 3, it can be determined that the least common multiple, LCM, between them will be 6. We will inscribe this numeral 6 in this location precisely above the arrow symbol. This is his common multiple for oxygen. Moreover, let's make sure we underline the oxygen formula on the left and right so we don't get confused. Now what do we have to do next? All right, we have discovered the common multiple. Now we have to split this common multiple first by the index of the oxygen element on the left side and then accordingly on the right side. So in the case of discussing the left side, we will divide the common multiple of 6 by 2 and obtain the number 3 as the result of the division. And we set this number 3 as a coefficient in this location. Now what do we have on the right side? On the right side, we divide the least common multiple, LCM, of oxygen by 3 and obtain the result of 2. And we put this 2 in front of the aluminum 2.3 formula. What's the worst way to do it? You can't stick this 2 inside the formula. That's just not acceptable. Inside the formula, there can't be any other numbers except for the indices. All right, we're good. We've equalized the oxygen. Let's move on. Next, we're starting, in this case, our coefficients are set, and in this case, we ended up with a coefficient of 3 on the left side and a coefficient of 2 on the right side in front of the element that contains oxygen. Here he is like a simple substance, here as part of a complex. Now, after we've equalized the oxygen, we move on to the next element. The next element is aluminium. So for aluminium, the atomic number on the left side is 1, and on the right side it is 4. Then the common multiple for aluminium will be 4. Let us proceed to sign it from the bottom as instructed. Now we start dividing the least common multiple. For aluminum, we divide 4 by 1. So, you are indicating that if we perform division operation on 4 divided by 1, the outcome we obtain is 4 as the result. We are putting this quartet up for aluminum. Next, on the right side, 4. To determine the amount of aluminum, we divide the aluminum index on the right by 2, resulting in a value of 2. However, since we already have a value of 2, we can conclude that we also have 4 units of aluminum. To validate this, we need to examine both the left and right sides of the equation. Starting from the left side, we find that we have 4 units of aluminum. Similarly, when we check from the right side, we also find that we have 4 units of aluminum. Therefore, the total amount of aluminum is 4 units. It is crucial to perform this verification in writing to ensure accuracy and avoid any miscalculations or discrepancies. And here is 4 and here is 4. Now we have a total of 6 oxygen atoms on the left side of the equation. 3 multiplied by 2 equals 6. Additionally, on the right side, we also have 6 oxygen atoms. 2 times 3. All right, our equation is equated. The equation is supposed to be read. Let's check it out. 4 aluminum plus 3 O2 equals 2 aluminum 2O3. So, I hope it is clear how we balance this chemical reaction. Let's perform the same operation on the next example. But now let's consider a different type of reaction interaction as an example to further illustrate the concept. All right, so let's have this interaction that's all about breaking things down. For instance, if we consider P2O5, which stands for phosphorus oxide, then under specific conditions, it has the ability to decompose into phosphorus and oxygen when subjected to heat. Okay, as the first step, we need to begin balancing from the element with the greater index, which is oxygen in this case. On the left side there's 5, and on the right side there's 2, but for oxygen, 5 is the biggest index compared to phosphorus. So what do we do next? We are doing the same thing as in the previous example. In the range of 5 and 2, we identify the least common multiple for this element through careful analysis. This will be a multiple of 10. Write 10 above the arrow. Now, moving on, what do we do with this number 10, the smallest multiple? We start dividing 1 by 1. And we start with oxygen, naturally. So then 10, the least common multiple, we divide by the index 5, which we have on the left side, and as a result of division, we get 2. 2 is set as the coefficient in front of the P2O5 formula. Following that, on the right side at this particular moment, we divide the total that is divisible by 10 by the index 2, and we obtain a value of 5. Place it in this location, buddy. As a result, we ended up with coefficients of 2, and we obtained a coefficient of 5. And please note, the 5 cannot stand in front of phosphorus because that is the coefficient specifically designated for oxygen in this context. So don't take it as if when we equate oxygen, and if formally here the coefficient is placed as if in front of this formula, it doesn't mean that this coefficient applies only to phosphorus. He's both phosphorus and oxygen. But in this case, we're putting oxygen on the same level as you. Now we will carry out the same task. Let's perform it for phosphorus. Okay, phosphorus is the next element in line. Okay, we have a total of 4 phosphorus atoms on the left side and 1 phosphorus atom on the right side. The multiple for phosphorus will be 4. Now we're doing the same thing. Consequently, in accordance with this reasoning, we proceed to divide 4, resulting in a quotient of 2, and subsequently obtain a double of that value. And that's exactly where we have a failing grade. This coefficient stays the same. Now, what about on the right side? The division of the number 4 by the number 1 yields a quotient of 4 when we calculate it. We assigned the value of 4 as the coefficient in front of phosphorus. Now, let's verify and make sure. Okay, let's focus on the left side. Therefore, in this particular case, it turns out that the value of phosphorus is 2 multiplied by 2, which gives us a total of 4. And simultaneously on the right side, we also have phosphorus. Therefore, the product of 4 multiplied by 1 is still 4. So, phosphorus is in balance. Just got to check the oxygen now. When you multiply 5 by 2, you get 10 oxygen on the left. And on the right side, the multiplication of oxygen by 5 also results in the value of 10. Our equation is equated. The equation is supposed to be read. Let's read this. 2P2O5 is equal to 4P plus 5O2. So the method we use to balance these two examples today is called the least common multiple. This method is truly excellent as it enables you to manage both straightforward reactions and more intricate reaction equations. That is why I highly suggest this technique to you because it functions really well in real-world situations. But sometimes this method doesn't always work, so let's take a look at some other ways to even things out together. Well, these techniques and examples I hope you understand. Goodbye.